Hey, today we're going to talk about 9.1, Stratospheric Ozone Depletion. So take a moment, check out the Enduring Understanding, look at the learning objective, pause the video, review the essential knowledge, and set up your Cornell notes. So recall that there's two different places where you can find ozone in the atmosphere. And we have the stratospheric ozone layer, which is the beneficial ozone, and we have tropospheric ozone, which is an air pollutant, a secondary air pollutant, that is formed through the actions of volatile organic compounds, nitrogen oxides, reacting with sunlight and oxygen. And it is caused basically by fossil fuel combustion, most notably internal combustion automobile engines. So the ultraviolet radiation, there are three different types, and they're basically, what you must know is how they interact with the ozone layer. The UVA just penetrates through, it is not blocked by the ozone layer. UVB is blocked but not entirely by the ozone layer, and UVC is blocked by the ozone layer, and that is a good thing because the human impacts of ultraviolet radiation, UVA can lead to skin aging, too much UVB can lead to skin cancer, and if you get hit with UVC, it will burn your skin severely. Environmentally speaking, ultraviolet radiation can disrupt photosynthesis if the ozone layer was not present. Ultraviolet or UVB can damage the DNA in plants and other organisms, and if any cells get hit with ultraviolet C or UVC, the cells will die. And this is why we use ultraviolet for sterilization. This is the form of UV that we use when we're sterilizing the effluent from a wastewater treatment plant. So some of the chemistry, and basically remember that ozone is it's not a very stable molecule. So it just takes a little bit of energy and it's going to break apart. So you have the sunlight. Sunlight has ultraviolet B and C, and the energy from those ultraviolet rays are received by the ozone molecule, give it a little jolt, and they break off the oxygen. And those oxygen radicals is what they're called. They're basically just an oxygen atom, are very reactive, and they will join together. O2 is very stable. Now another thing, the sunlight will hit an oxygen or an O2, and there is enough energy in that UVB and that UVC that will cause this oxygen, this very stable oxygen, diatomic oxygen molecule, to break apart, and it can reform into ozone. So this is a cycle that happens, and it will just continue to happen naturally in the stratosphere. Now here's the problem. Chlorofluorocarbons were originally created. They're completely anthropogenic. They do not exist naturally. They are created as refrigerants and propellants. So in air conditioners and refrigerators, there used to be CFCs present. So you might not have to know. I mean, I would basically understand chlorofluorocarbons, but if you don't remember that and you can't spell it or you're scared to write it, you can also write CFC. So either understand the name correctly or remember the acronyms, because there's going to be other acronyms in upcoming videos. I would basically, the structures are not important, but this represents carbon. These blue ones represent fluorine. These represent chlorine. So this would be CF2Cl2. This would be CFCl3. Now, how does a chlorofluorocarbon destroy the ozone layer? So you have a random CFC that elevates itself and floats up into the stratosphere. Well, where it encounters those UVB and UVC rays, and it absorbs energy from the sun, releasing that chlorine molecule. Now that chlorine molecule, that's really damaging. So remember that the chlorine is the one that is really messing up the party. So what happens is that chlorine goes over by an ozone, picks up that oxygen, forms ClO, which is not very stable, and another chlorine, just for these purposes, there's another one. Let's say there's another CFC somewhere else. It goes and picks up another latches onto an oxygen on another ozone molecule, picks it up, and then notice we have two O's. They get near each other and they form an O2. Now, that might seem nice. However, we're losing our O3, our ozone, and these chlorines, these highly reactive chlorines, can now do the same thing again. So now they find another ozone, break those apart. Oh, let's make another oxygen. Okay. So it'll keep doing this and breaking these apart, and the chlorines will go back and find another ozone molecule to destroy. So the big problem is one of these chlorine molecules can persist for 50 to 100 years, or one of these chlorine atoms, my bad. And one chlorine atom can destroy 100,000 ozone molecules. So when you think about how many CFCs were released into the atmosphere through the actions of leaking refrigerants or these air conditioners, eventually there was a hole in the ozone layer. And the hole in the ozone layer formed over the South Pole, over Antarctica, and there is natural depletion of ozone. And the chlorofluorocarbons helped to exacerbate that. They made it worse, and it would show up, the hole would get bigger during Antarctic spring. So naturally, there is a slight thinning of the ozone layer during Antarctic spring, which is October. So it would be, our spring is obviously in March and April. This is the southern hemisphere, so it is reversed. So a couple of things which you don't have to know too much about the chemistry here, a lot about the science, but what you should know is that there are clouds, polar stratospheric clouds. I know way back in the beginning of the year when we were talking about, or in the earlier part of the year, we were talking about all of the weather occurs in the troposphere. This is the only exception. Very high, where it is super cold, you have water and you have nitric acid that exists way up there. And what happens is chlorine gets released, binds to that nitric acid, becomes chlorine nitrate, and then you have HCl, which who cares? You don't really have to know this formula, you don't have to know this equation, but I'm just explaining what's happening. And when you have this chlorine that is up in the atmosphere, it will get hit by the UV rays and it will dissociate. And once you have this Cl, you can go and break apart the ozone molecules like I showed you in the other slides. So basically what happens is you have chlorine that gets naturally released. This is how it's up there. It happens under super cold conditions. So that's the takeaway. Stratosphere, Antarctic, spring, super cold, chlorine gets released and breaks up the ozone naturally. This process is mainly only done during the Antarctic spring, and that's basically all you have to know about natural ozone depletion. So, what I would like you to do for this FRQ practice is explain how CFCs can destroy stratospheric ozone. I hope that this video was informative. I hope you took down all the chemistry because you're going to need to know it, especially for this question. Thank you very much for your attention. I will see you soon.